as the question says, find the mass m of the hanging block in figure which will prevent the smaller block from slipping over the triangular block. All the surfaces are frictionless and the strings and the pulleys are light. Now first, let us understand this problem. The thing is that this block of mass m will move downwards, providing this wedge and this block with some acceleration in the right direction, and which will provide some pseudo force over this block and which may prevent this block from slipping over this wedge at a certain value. We need to find out that specific value of acceleration, and further with the help of that acceleration we will find this mass capital M. So let us assume that this system is moving ahead with an acceleration of small a. So obviously this block of mass capital M will be moving down with an acceleration of small a. So this in turn will be applying a pseudo force of small m into a in the opposite direction of motion, that is in the left direction. Now let us also assume the tension T in the string, and let us also assume that the normal force N, that is the contact force N, is acting between the wedge and the block of mass small m. Now we can draw the free body diagram for the small block of mass small m. So we can show it as a small block of mass m having an mg force in the downward direction, a normal reaction N at an angle of theta with the vertical, and an MA force in the left direction. Now how we got this angle theta is, since we are having this angle as theta, this angle will be theta as the alternate interior angles. This will be 90 minus theta. So obviously this will be theta. Now we can balance the forces over here in order to avoid the slipping of this block over the wedge. So framing the equations, due to the horizontal balancing of the forces, we can say that n sine theta equals to mass into acceleration. That is the first equation. And the second equation, that n cos theta equals to mg. Now from this we can say that n is equals to mg over cos theta. Marking it as equation number 2 and putting this value of normal in equation number 1, we get mg tan theta equals to mass into acceleration. Cancelling the factor of m on both the sides, we get acceleration equals to g tan theta. Let us mark it as equation number 3. Now let us move forward for the FBD of the wedge. Let us assume it to be a block of m dash direction having a normal reaction of n at an angle of theta with the vertical, and having a tension T in the right direction. We are not showing the normal reaction and the m dash g forces over here because we need to balance it out only in the horizontal direction. It is having an acceleration of a in the right direction, so we can write it as m dash into a equals to tension T minus n sine theta. Now make sure, or rather Put it in your mind that we didn't take any acceleration for this block small m, though it is moving along with the wedge, because we took into consideration the pseudo force. So there was no requirement of any acceleration A of the block. Coming back to our equation of the wedge, we can put the value of acceleration A and the normal from equation 2 and 3 into this equation. So we can write it as m dash g tan theta equals to tension T minus small mg tan theta. And marking this equation as equation number 4, let us proceed with the free body diagram of the block of mass capital M. We can show it as a block of mass capital M moving down with an acceleration of A, having an mg force in the downward direction and a tension capital T in the upward direction. So we can frame the equation as capital M A equals to mg minus T. We can put the value of A over here. We can write it as mg tan theta from equation number 3 equals to mg minus T. Now putting the value of tension from this equation into equation number 4, we get m dash g tan theta equals to mg minus mg tan theta minus small mg tan theta. Let us make it in a more systematical or rather useful manner. We can write it as this equals to m dash g tan theta plus small mg tan theta. Now cancelling the factor of g from both the sides, we can write it as capital M equals to m dash plus small m into tan theta over 1 minus tan theta, which is the answer for this question. Now in this question you could take another way of solving also, like you could have avoided this pseudo force and taken that acceleration into consideration. I needed to avoid that, so I preferred this way of taking pseudo force into consideration. Now in such type of questions, always remember that in all the competitive exams or everywhere where you need to solve these type of questions, your basic aim is to save your time. So avoid making the unnecessary additions to the free body diagrams, that I didn't mention any normal or the mg forces because I had to do nothing with that. I needed the equation only in the horizontal direction, and so I didn't mention that.